Good morning, everyone. This is Mr. DHAKSHUNHAAMOORTHY, AP, AIML department. Today's topic is gradient descent method in unit function approximation. Value function approximation. Why we are using gradient method, that is what we are going to discuss in this topic. Challenge 1. In real world problems, state space can be large and backgammon. Here number of states 10 power 20 states. Another game, computer go. Here we are using 10 power 170 states. Robot harm, there are infinite number of states, continuously it is coming. Problems with a large number of states, there we are using MDP. There are too many states and are actions to store in memory, that is very problematic one. Another one, it is too slow to learn the value of each state immediately. Need for the value function approximation. So far we have been assuming that all the function value, state value or the action value can be represented as stable. Only if the state and action space are small, the tabular representation are linear in state space and polynomial in action space in both time and memory. In many real world problems have large state and action space, that tabular representation is insufficient. Example, backgammon just before we seen 10 power 20 states, and computer go, another game that is 10 power 170 states. Approximation function. Problem space, it is further assumed that the states x are the quasi-continuous and the action u are discrete. Where states are x, that is quasi-continuous, and the action u are discrete. Today's focus, the value-based control task, transferring the established tabular methods to work with the function approximation. Hence, we need to extend the previous prediction methods to action values. Q of Ax, u, w, that means state, u is the action, w is the weight, is approximately q pi of x, u. And apply the well-known generalized policy iteration scheme to find the optimal actions. Q of x, u, w is approximately q star of x, u. Function approximators. There are many that are considered in literature, like linear function approximations, neural networks, decision trees, nearest neighbors, Fourier and wavelet bases. Commonly differentiable functions approximators are considered. For examples are linear function approximators and neural networks. Stochastic gradient descent. Stochastic gradient descent, SGD, is the basis behind the value function approximation. We need to define the error function parameterized by W. Objective, find the local minima of error function, usually by gradient descent. Weight W is updated with the previous weight minus alpha into gradient of error square. Here alpha is the step size parameter or learning rate. All deep learning packages have automatic differentiation. The gradient descent and the delta rule, there we can able to see this here. The linearly separable line, both the symbols are uniformly separated, whereas non-linearly separated, here some mixing of symbols is available, even then we are separating with the linear line. it cannot be separated with one single line, because some symbol, the plus symbols along with the minus is grouped one side, and minus symbol along with the plus symbol is grouped another side. This one is non-linear separable. And gradient descent and delta rule, here the gradient value is keep on reduced. At one point we are getting the expected value and the maximum the efficiency. Gradient descent and delta rule. Perception rule finds a successful vector weight vector when the training examples are linearly separable, but it can fail to converge if the examples are not linearly separable. A second training rule called delta rule is designed to overcome this difficulty. If the training examples are not linearly separable, the delta rule converges toward a best fit approximation to the target concept. The key idea behind the delta rule is used to gradient descent to search the hypothesis space of possible weight vectors to find vectors that best fit the training examples. This rule is important because the gradient descent provides the basis for the back propagation algorithm, which can learn networks with many interconnected units. It is also important because the gradient descent can serve as basis for learning algorithms that must search through hypothesis spaces containing many different types of continuously parameterized hypotheses. Gradient descent and the delta rule, here how we can calculate the direction of the steepest descent along the error surface. This direction can be found by computing the derivative of E with respect to each component of the vector W. Vector derivative is also called the gradient of E with respect to weight vector, written as gradient of E of weight vector. Gradient of E of weight vector is nothing but dou E by omega, dou omega naught, dou E by dou omega 1, and dou E by dou omega n. Since the gradient specifies the direction of steepest increase of E, the training rule for the gradient descent is weighted vector is equal to weighted vector of the current state plus the small variation, change in weight, where change in that weight is nothing but minus eta into gradient of E of W, where eta is the learning rate. Here eta is the positive constant called learning rate, which determines the step size in the gradient descent such. The negative sign present because we want to move the weight vector in the direction that decreases E. The training rule can also be written in the component form Wi plus equal to Wi plus change in weight. Then the small change in weight is nothing but minus eta into dou E by dou omega I. Gradient descent and delta rule. Dou E by dou omega I is nothing but dou E by dou omega I, where E that is equal to half of summation of TD minus OD, that means target value minus observed value the whole square. Here small change in weight is equal to minus eta into dou E by dou omega I, where eta is learning rate. We are substituting in this change in weight E value in the changing weight equation, so that del omega I is equal to eta into sum of the D is subset of capital D and here TD minus OD is the difference, target value observed value difference into XID. Then the updated weight WI is equal to the current weight plus the change in weight. The gradient descent, let J of W be a differentiable function of parameter vector W. Define the gradient of JW to be gradient W into J of W. Here the derivative of dou JW by dou omega 1 J dou J omega W divided by dou omega 2 J dou JW of dou omega n is the space they shown here. Goal to minimize J of W. Method, move W in the direction of negative gradient. Del W is equal to minus half into alpha gradient W in J of W, where alpha is the step size parameter. Approximate values by the stochastic gradient descent. Goal, find W that minimize the difference between VW of S and V pi of S. J of W is equal to expectation of V pi of S minus VW of S the whole square, where D is the distribution over states. The gradient descent change in weight del W is equal to minus of alpha gradient W JW. That means alpha into expectation of V pi of S minus VW of S into gradient W and VW of S. Stochastic gradient descent SGD, sample the gradient. Change in weight gradient del W is equal to alpha into GT minus VW of ST and gradient W VW of ST. Note, Monte Carlo written GT, where is a sample for V pi of ST. Stochastic gradient descent SGD is a popular optimization algorithm used in machine learning and deep learning for minimizing the loss functions. It's particularly useful when dealing with the large data sets because it updates the model parameter based on a single example or the small subset of examples rather than the entire data set, which can be computationally expensive. SGD algorithm initialize the parameters, start with the initial values for the parameters of model, often randomly chosen, iterative until converge. For each approach, shuffle the training data to ensure randomness. For each training examples, compute the gradient of loss function with respect to the model parameter using the current training example. Update the model parameters in the negative direction of the gradient to minimize the loss function. Repeat this iteration, continue iterating until the algorithm converges or until the predefined number of approaches is reached. Here simplified example of how SGD works using linear regression. Here suppose we have a data set of data points xi, x1 y1, x2 y2 dot xn yn, and we want to fit the linear model y is equal to mx plus b to this data. The loss function we want to minimize is the mean squared error MSE. Mean squared error MSE is equal to 1 by n summation I is equal to 1 to n yi minus mxi plus b the whole square. The gradient of MSE with respect to the parameters m and b are dou MSE by dou m. That means gradient of MSE with respect to m minus after taking derivation with respect to dou m minus 2 by n summation I is equal to 1 to n xi into yi minus mxi plus b. The gradient of MSE with respect to b, dou MSE by dou b, is equal to minus 2 by n summation I is equal to 1 to n yi minus mxi plus b. Now we will use SGD to minimize this loss function. Initialize the parameters, randomly initialize m and b. Iterate until convergence. For each approach, supple the data set. For each data point xi and yi, compute the gradient of loss function with respect to m and b using the current data point. Update the parameters. M is equal to m minus alpha dou msc by dou m, and b is equal to b minus alpha into dou msc by dou b, where alpha is the learning rate hyperparameter that controls the step size. Repeat until the convergence or for a fixed number of approaches. This process continues until algorithm converges, and example, until the changes in m and b become very small, or until maximum number of approaches is reached. The SGD is a fundamental optimization algorithm used in many machine learning models, including neural networks, logistic regression, support vector machines. Its stochastic nature allows it to escape local minima and to converge faster, especially in the high dimensional spaces. Thank you.